All right, I'm Sam. This is my ADC talk, Aliasing, Oversampling, and You. First of all, who am I? I am the technical co-founder of a company called Music Hack. We make a plugin called Master Plan. You should check it out. I am a lifetime computer musician and composer, all the way back from DOS-based things to today. I'm also a programmer because that's what I did to make money for many years, and eventually I just sort of married the two. So I have a couple decades of various coding experience from embedded systems to web development, and finally I ended up here because it is the most interesting and fun to me. And what am I going to talk about? We're going to talk about aliasing distortion. We're going to talk about the ways that you address it most commonly. That's through oversampling. It's not the only way. And I'm making this a big-intermediate talk, so we are not going to go over a lot of math and code. Instead, I want it to be really easy for you to understand the concepts that we're working with here, because there's just a lot. And in order to make good decisions about what we're doing, having a great understanding kind of conceptually, I think, is sometimes more important than knowing the math, because oftentimes we're in positions when we're using other people's libraries and not writing our own DSP code. Not that there's anything wrong with it. So I'm going to start with what sampling is. So I have up here, we're going to talk about the Nyquist-Shannon sampling theory. I'm going to go over it really quick with pictures instead of math. But basically, it says that if we have a signal, and that signal does not have any frequency content that's above half the sample rate, that's what's called the Nyquist frequency, then we can sample that signal and then reconstruct it perfectly. But we do this by summing sync functions. I have a picture of a sync function at the bottom that are centered and scaled per the sample, right? Now, this is ideal, right? Because the sync function goes infinitely backward and forward in time, and we only have finite processing time in a computer. So everything we do is a compromise that's making one sort of sacrifice in order to get another thing better, depending on what exactly we're trying to do. Okay, cool. Let's take a look at what this looks like. Let's say we have a waveform, and we sample that waveform with a sampling rate that's good enough that the waveform is under our Nyquist frequency. This is what a sync function might look like if we were to center and scale it at one point. And we just repeat this process for all of the points, and then we sum them anywhere we want. You may use this if you're writing a resampler or whatever. You might have heard of windowed sync interpolation. That's just sync interpolation, but we cut a little window out of it because, again, we can't go infinitely backward and forward in time. We have some number of approximation ways to do this. And we end up with a signal that's basically where we started with. So that's pretty awesome. And the way that we record audio, we always have an anti-aliasing filter on the way in so that when we digitize the samples, we haven't caused any problems. And on the way out, and this is pretty interesting, the low-pass filter actually does the reconstruction between the samples. That's a pretty interesting way to go. I mean, there's all kinds of DACs. Delta sigma is the big thing now, but you know, we've got to start somewhere. Now, the question is, what happens when we try to record a signal where we have content that's above the Nyquist frequency? Well, things get a little dirty. It starts okay, but as the distance between the points go apart, the waveform just starts to get all messed up, right? We don't have enough points to represent the waveform that we tried to record. And, you know, it just does not look very pretty right there. That is what aliasing is, all right? So aliasing, oh, the wheel's not spinning. Oh, there, it's, unfortunately, that's not aliasing, that's just network lag. But I have a roulette wheel there because aliasing is very similar to what we call the wagon wheel effect. If you've ever looked at a car or a bicycle and the wheel starts spinning really fast and it starts to spin so fast that your brain cannot interpret what's going on, it'll start to look like it's going backwards or stop. That's aliasing, same concept, right? We have some amount of speed, we can figure things out, and if it goes beyond that, we can't catch it in time. I'm now going to play you a sample of what aliasing sounds like. Oh, there we go. You can see that the ball looks like it's going a different direction than the numbers. It's not. That's aliasing. So I'm going to play a sine sweep for you that goes from very low to very high. It's going to be really annoying and painful, but rest assured the sine sweep only goes one direction. And I'm going to do some DSP to it that causes aliasing. You're going to hear what it sounds like. You ready? right? So it starts to bounce up and down. The reason is when you hit the Nyquist frequency, the frequency that you get back from your recording is going to start going back down towards 0, and it'll start bouncing up and again as your frequency keeps getting higher and higher. I'm going to give you a second representation of this real quick, just to really hammer in the concept. Let's say you're dribbling a basketball, right? You're sampling 12 hertz, you're dribbling 6 hertz. We can just be like, oh, look, here we go, up, down, up, down, up, down. We can sample it, right? We have enough resolution to talk about what's going on. But as you start dribbling the basketball faster and faster, you might only get 1 sample per cycle, or 2 samples per cycle. So we can get a vague shape out of this, but that's kind of about it. When I say vague shape, it might be why if you make like a map-based wavetable oscillator, you start removing higher and higher frequencies till at the very top, your waveform is always going to look like a sine wave because you keep removing more and more high frequency content, right? Anyway, once you pass the Nyquist frequency, you get this big old mess. Your samples can't really represent what's going on, and it doesn't look anything like any sort of repeating wave there, or at least not what's actually happening, right? So now that we have some samples, let's talk about, I just want to do a little mental exercise. Let's just assume we've recorded the samples, it's good, we have some kind of thing we like, right? And I'm going to pick another weird sample right here. Let's say this is 16 hertz. I like weird numbers. Why are there 17 dots? Because I can't count. I said we're not going to do any math. If you were to sample a sine wave, it might look like this. I hope the contrast is enough. You can see the blue dots, right? That's all fine and good. So we could draw a sine wave in here, and it would look like something like this, right? And if we look at this, the question is this the only sine wave that might fit all of the blue dots? I'm going to zoom in. Why did the line get thinner when I zoom in? Because I don't really know illustration programs, but that's not the point. So we have this. So if we were to take what we have right here and increase the sample rate, given what we have, right? I'm going to represent that by adding more dots to it. Oops, go ahead. If we added more dots here and we try to resample it, we'd have a new problem. And that is, could there be another sine wave we could draw through all of these dots that would work? Well, we can't make a slower sine wave, right? Because if it were slower, it would stretch outward. And as soon as it stretches out, it's going to miss one of these dots, and then it'll never hit it again. No amount of stretching is going to fix that. But if we make it faster, eventually, we'll end up with a sine wave that fits all the very same dots, right? So it's ambiguous if we have a waveform and we're going up to more samples, or maybe even to analog, like the continuous waveform. Which is it? All right, I said no math, but we'll do a little bit of math here real quick. Let's just count. There's 1 blue cycle and there's 3 orange cycles, right? That's cool. 3 times 4 is 12 hertz. So if we had 4 hertz and 12 hertz, everyone in agreement with that? That's cool? All right, our Nyquist frequency is going to be half of our sampling rate, which I said was 16 hertz. So that's 8. 12 is greater than 8. If we subtract it, we get 4. So we go up to the Nyquist frequency and we bounce backward 4, and we come right back to where we came from, right? What does that mean? We come full circle. So at this sample rate, any line that's faster than 4 hertz, but that goes through all our little blue dots, is going to alias right back onto our original sine wave. It's kind of a cool little thing there. But if we upsample to a higher rate, were our samples intended to represent the blue wave, or are they intended to represent the orange wave, right? This is another problem that we're solving. I want you to pack this in your heads, and we're going to talk about something else really quick. So all right, we're stuck at the upsampling phase. And we're going to talk about another thing really quickly, which is, hold on a minute. We just said, okay, if you've band limited your signal, if you've taken out the high frequencies, how all of a sudden do I have new high frequencies that are aliasing? How is this a problem for me as a plugin developer? Because I'm just handed a waveform. Well, the problem is nonlinear math, right? So we'll get into that in a second, but the reason we love nonlinear math is that linear math often, people will tell us it sounds boring. It's kind of funny because for decades and decades, electronic engineers that are designing these hardware products that we all love are trying to make them as linear as possible. And then as soon as we can do perfect math in the box, we're like, it's too linear, we have to go the other way, right? So this math exists to make our plugins sound great, so we're using it all the time. And that is what causes distortion. What goes in is not the same as what comes out, and that distortion has higher frequency content, which can't be represented by the sample rate that we're using, and that's how we as plugin developers using DSP math create this aliasing. We create these higher harmonics that then bounce off Nyquist, right? What is nonlinearity? Basically, it's any math that doesn't look like a line, right? So if you multiply something, if you add something, if you multiply and add something, that's fine, you're good. There's no distortion that's going to add to your signal. But if you throw something through a hyperbolic function like tan H, right? Atan, these really common ones we see, squaring, cubing, all this stuff, those are all nonlinear. If you were to draw a math, there'd be a curve in it. If you draw a graph, there'd be a curve in it. And so that's going to cause higher harmonics, right? So let's talk about the shapes that we have, different kinds of distortion, right? There's harmonic distortion. This is distortion, well, we'll get to that in a second. We have harmonic distortion that exists in the analog and in the digital realm, right? So if you have a piece of gear, you run something through it, it's also gonna have harmonic distortion, right? That's what's pleasing about it. It's why people always talk about tubes and their even harmonics, right? We have intermodulation distortion. This is a real nasty bugger. I'll give you an example of it in a minute, but that's also analog and digital. You'll hear people say, oh, aliasing doesn't matter, intermodulation matters. You're like, there's different planes of existence. We'll talk about that in a minute, but it's also analog. So we may or may not like the intermodulation distortion we get, but if we're trying to model something that's analog, that's part of the deal. It's part of the package. But aliasing is digital only. It's a byproduct of sampling itself. So we really need to, if we want to make something have that kind of sound, oftentimes we're trying to get rid of it, right? It's a particular problem. Now, this isn't to say that we always want to get rid of it. There are some digital artifacts we love. There's some effects that intentionally alias because it's great sounding distortion. That's cool. So harmonic distortion just means it follows the harmonic series. Your signal's frequencies multiplied by 2, 3, 4, 5, 6, all the numbers. So if you start at 300 hertz, you'll get 6, 9, 12, all that. And then there's odd harmonics versus even harmonics. That doesn't matter too much for the sake of this talk, but different trigonometric functions will give, or not even just all kinds of functions will give you different kind of characteristics of their distortion. So when you see that there's 300 million different saturation plugins that are at play, like they all have these different combinations of them, right? So real signals, however, they're never just a pure sine wave. We've got a whole bunch of stuff going on. So it's kind of weird to just talk about even in odd harmonics because what we get out of everything is a whole package deal. Let's take a look at what this might look like and listen to some harmonic distortion. That's pretty subtle in this sound. Oh, there we go. So it's kind of got this clean sound. You just hear a little bit of higher frequencies in there. And we have some odd harmonics that will show up on a spectrogram. This is going through a tan H function, which is used fairly often. Intermodulation distortion is way grosser. It basically is the sum and the difference of each component frequency. So harmonic is nice because you always end up with something that's musically related to the material that you're working on. But it'd be weird if you could just be like, oh, if I do something that just generates the second harmonic, I have a perfect pitch shifter, I'm done, right? Like that doesn't work, obviously. And it's because of, well, intermodulation distortion is part of that. And it's inharmonic because we're adding frequencies which are in a log domain, so it gets ugly. And worse than that, the intermodulation distortion itself causes more intermodulation distortion. So after you get the sum and difference, you have the sum and difference of the sums and differences, and they propagate like wild. And it sounds a little different. So if we have two different frequencies that are each going through our tan H distortion here, they might look like this if you were to look at each chart separately. But if we were to sum them and then put them through tan H distortion, we get this. Oh, yeah. So it's like if your dog tried to make a DX7 patch, it would sound, kind of like that. Not pretty, right? So intermodulation distortion, not pretty. But what does this have to do with aliasing, right? So the deal is that you get higher harmonics from all of this stuff that's going on, from the intermodulation distortion and from the harmonic distortion. And these harmonics are what climb way too high and they start bouncing off of your Nyquist frequency because the samples can't represent what the distortion was trying to do to the sound that you had, okay? So this chart right here, it's a little tricky at first, but let's see if we can get used to it. The lowest pink line, or it's like a mix between purple, it's like a fuchsia, the lowest fuchsia line is your original signal. And I just put two harmonics here, the second and fourth. And by the way, this is a really clean chart because I'm not doing any intermodulation distortion here. So the real picture for whatever audio you have is way crazier than this. But I just, for the sake of example. So we'll start with this. If we add two harmonics, they would like to go here, right? But we can't go there. We don't have a sample rate where the Nyquist is that high. If we have 48K, our sample rate's gonna be 24K, right? So what happens is we get this aliasing and it starts bouncing off, and all this blue stuff is aliasing noise. And this is the stuff that we're trying to get rid of. Yes, so let's see how this would work. On the left, we have our original graph. And what happens if we raise that ceiling that we bounce off of? We up the sample rate, we get a higher Nyquist. It's cool. It's a lot less aliasing now because there's more breathing room for the frequencies to move. This is great. This is just with 2 times oversampling. So you can imagine the more oversampling you do, the longer it takes for a frequency to climb up and bounce off the ceiling. And at the end of this, we obviously need to go back to the sample rate we're intending to process at. So we put a filter on it, and we're left with just that little tiny blue band over on the right, which is a much better situation. So we can see that we oversample, then do the nonlinear math, then we filter it, and then we rip our samples back out so we have the original amount. And you can also see that you get more than 1 octave because you are also going to be removing the top half of this guy over here when you low pass filter. So it's a really good solution. And this will work for anything that's causing distortion due to the nonlinear math, right? So again, we increase the sample rate for a new Nyquist. We interpolate to fill in the samples. We perform nonlinear processing. We filter above our old Nyquist frequency. Then we just simply remove the samples. So why don't we take a look at how this works? We're gonna start by 0 stuffing between the samples. So you got a bunch of samples. We want to double the sample rate. You just put zeros in between them. That's pretty great. Whatever engine you pick, it's going to do something like this. But then we do what's called a low-pass interpolation filter. I'm going to get into that in a second. But this is just a very high-quality way, if you're at an integer rate, of interpolating between the samples so that we can then work with them without noise. Now, let's say we're starting with this. Now, this is a ridiculous chart, I know, because the left side has nothing to do with the right side in terms of its content, but I just need an illustrative example, right? So on the left, we have the time domain representation of a sine wave. On the right, we have a frequency domain representation of like an entire musical signal, and that's fine. So the next thing we do is we do some 0 stuffing. So I've represented that with there's more white points in between here. And now we're gonna come back to what I told you to store in your head. What do we do with the new samples that we have, right? We need something that's going to be able to interpolate between these two things and know kind of what was intended by the samples that we currently have. And the way that this presents itself when we look in the spectral domain is called the spectral mirror. Evil Kermit, look at you back in the face. Now, the reason I've gone through all this trouble to go this way is I want you to know that the spectral mirror is always there. It's not added by the 0 stuffing. It's not like there's some other technique that will suddenly not give you the spectral mirror. Like, it's exposed by the fact that you're upping the sample rate and don't have enough information, In any case, we have to solve this problem. The math here is real quick. Just if you have 1 kilohertz, it'll show up. I'm just illustrating the mirror aspect at the top minus 1 kilohertz. So if you have that, if you oversample to 48K, you'd have it 1 kilohertz, and its representation in the mirror would be at 47K. Now, this is important because something we haven't talked about yet is I played you a sine sweep, right? And we didn't really hear anything weird until we got really, really high up, right? But signals that we process on a day-to-day basis that our customers are using, whatever the application, they really do not have a lot of high frequency content that's super loud. Like, I don't know the last time I've ever seen anything that had like 0 dB at 17 kilohertz. Like, that would be, my dog would bite me. But yeah, but the spectral mirror is a different problem. It's been flipped. So all of the loud frequencies are right up towards the top. And what that's gonna do is mean that as soon as you start doing any nonlinear math, they're gonna come barreling back down into your audible frequency, right? So your interpolation filter, the thing that goes between the samples and also cuts off the spectral mirror is hugely important because you need to cut those out. Okay. Oh, that was what this slide was about. So after we've done all of that, the way that we reinterpolate is through a low-pass filter. That's how we make sure that we don't have the secondary, like high orange signal come through. Remember we talked about sync interpolation? Well, it just so happens that a low-pass filter's impulse response looks an awful lot like a sync function, which is why it works. In fact, any time that we're trying to do some kind of interpolation or do this sort of stuff, it's some level of approximation of doing sync interpolation. It's just different math. Then we simply remove all the in-between samples and we're done, right? So it seems pretty straightforward. Also, you've got to pick what your sample rates are going to be, right? So depending on the process that you're doing, do you want 2, 4, 8, 16 times oversampling? This is going to be specific to what it is you're trying to oversample and what you measurably hear or don't hear when you're listening. And it's really important to use your ears when you do this because you may not need to oversample at all. And we'll talk a little bit later about this, but sometimes it has a lot more to do with what your users are requesting than what you're able to hear, even in really great listening environments. And that's going to be a struggle for you if you have that kind of customer. So that's really a business decision at that point, but it's something to think about. The last point here, I just basically mean we often use the same filter to interpolate as we do to decimate later. It's just, it's efficient, it's easy, and generally our needs are the same. So the real difficulty in all of this is the rabbit hole of filter design, right? So filter design is like, we could ask 100 million questions about all this stuff, and anyone who's worked on an EQ or on whatever has had to deal with this a lot. And lucky for us, there's a lot of different things that are available to us. Oh, it's loading. Well, in any case, don't freak out about it. You don't need to know everything. The practical implications of what you're doing matter a lot more than theoretically what might be best. You just need to do things and measure. And you need to start with what your specific needs are, and then you can optimize and like kind of get down into the nitty gritty. And that's a really important point. If you go looking for like the highest performance X, Y, and Z before you know, because again, audio is often about making compromises, before you know what thing you want to optimize for, it's gonna be a waste of your time. So start with the big wins. And the first thing is to ask yourself whether or not latency is important to you. This, I think, is even in the JUICE documentation, but you're going to be making a base decision in the beginning of whether you use minimum phase filters, IIR filters, or if you're gonna use linear phase filters, FIR filters. There's a bunch of trade-offs with all this stuff, but what it comes down to is if you care about latency, you're gonna wanna use an IIR filter because FIR filters that have great characteristics for a steep cutoff are going to just cause too much latency and some of the problems. Otherwise, I'm recommending that you use a linear phase filter because it keeps the signal as similar as possible to the original. And it also, in my case, for instance, I work on a mastering plugin. So headroom is a big deal for me, right? I'm at the end of a chain. So if you're gonna be doing that or show up right before some dynamics processing, it's a good idea to care about your headroom. And IIR filters tend to have more overshoot. That's the little ripple that shows up, like if you put a square wave and then I should have had an image of it. But in any case, so if you care about that, then an FIR filter will also be good. But the general rule is if latency matters, use IIR, otherwise use FIR. We'll talk about the CPU usage case a little bit later because usually this decision is the most important. And medium latency is, I don't really think it's a thing. Maybe you disagree, but it's like either latency matters or it doesn't. Once you've gone up to like 20 milliseconds, it may as well be 50 as far as I'm concerned, but I think depending on your application, that's it. I think for audio plugins, that tends to be the case. So let's talk about some of these decisions. So for IIR filters, or minimum phase filters, you get very low latency, but you start to have some phase issues in the high end. The phase will start to change, and you have more overshoot, so it's a problem for dynamics processing. Linear phase filters are gonna have better characteristics for the phase. Obviously, they're gonna have less overshoot, which is cool, but they're gonna have higher latency. And the CPU efficiency probably is worse for FIR, but like, it depends on all of the things you're getting. Like if you have your own filter processors or whatever, you tend to be able to optimize, yeah. Cutoff frequency is another thing you're gonna pick. You need to choose at what point am I gonna start eliminating frequencies for my spectral mirror because we can't make a perfect filter, right? So if you have a lower cutoff frequency, you're going to have something that's The real deal here is that if you have a lower cutoff frequency, you can have a shallower transition band, which is easier to compute. And as you push it up, your transition band gets steeper and steeper, which we'll talk about later. But the problem with a lower frequency is that you also start to cut off frequencies that are actually in the audible range if you're not careful. And this might be pretty subtle, but if you are a plugin that might be stacked with other things and everybody tends to make the same decision as you, someone might find out that they're actually getting high-end cut out of their signal because it was set too low. So it's not really great to pick a lower cutoff frequency unless your plugin already has a low-pass filter before you oversample. That may be the case, in which case this is a compromise you could make. Higher cutoff frequencies also have higher order because of the steepness, but we'll get into that now, which is the stop band attenuation. Oh, I'm sorry. One other thing, most of these oversampling solutions will have you specify a cutoff frequency as a factor of your sample rate. So if you wanted to have the cutoff exactly at the Nyquist, it'd be 0.5, right? So it might be 0.49 or whatever. So you'll have to look in the documentation for that. Stop band attenuation is just how much you want to cut down on the frequencies that are after the transition band. So when the filter's done cutting off its stuff, like how low did it go, right? We don't eliminate it, we just push it down as far as we can. So if it's a lower stop band attenuation, it's going to be a more efficient filter, it's going to be a lower order filter, but you're going to have less anti-aliasing because you're only going to push the high frequencies down a small amount, right? If you have a higher attenuation, you're going to have more anti-aliasing for some given cutoff that you pick, which is good, but it takes more compute power and there's more latency if you're using finite impulse response. So these are the trade-offs that you're going to make are in these tables when you're deciding what works for whatever application it is that you're making. And here's an important one, filter stage design. So the way that we talk about adding samples and filtering and adding samples and filtering, we tend to do oversampling in stages. There's another approach, again, which I'll go over briefly later, but as a result, we have to run our interpolation filter, then we sample again, then we zero stuff again and run another interpolation filter, then we zero stuff again, right? This happens in stages. And it's the opposite on the way back. We run a low-pass filter, we rip out some samples. We run another low-pass filter, we rip out some more samples, right? The first stage is the most important. I'm gonna show you why right here. So at first, we've generated, we have the spectral mirror that pops up, right? And in order to have our best control over what gets left over in that band, we want it to cut off as soon as possible because everything above there is not stuff we wanna have. For every extra frequency, it's gonna alias back into the audible range that much sooner. So we need a very steep filter, and because of the trade-offs I talked about earlier, we know that something that has a very steep transition band, as in it has a high cutoff with a really low or really intense attenuation, is gonna be really inefficient. So we don't wanna be doing the same filter every time because we'll be wasting CPU power, we'll be adding more latency, it's not a good thing, right? So after the first stage, our mirror looks a little different because we've already cut out we've already cut out the middle here. I don't know why I'm gesturing when I could just point here. So when we zero stuff again, the first half of the new spectral mirror is already taken care of for us, right? So we can have a shallower filter. And that's great because it means the second filter can be more computationally efficient, have leaner characteristics. That's awesome. And the good news is it gets better and better the more you oversample. Now, that starts to be replaced by the fact that you now have to process each thing, 4 times, 16 times. So it becomes less and less important in terms of performance, but it is important to know that these filters should not be the same because it's a waste of your resources. This is a concept that's really important to understand. I told you that I wasn't gonna show you any math, but I will show you a math in this slide. It doesn't matter what this math is. You can reference it later, but it's essentially the math equivalent of what this slide is showing you, right? So this is a great little handy reference. You can also find it in the README for HIIR, which is a great infinite impulse response library. But it's just basically saying that each oversampling stage, you have a shallower and shallower filter to be more efficient. Okay, so we've talked about a bunch of trade-offs. I wanna go over how you might pick an oversampling solution to start with because we're given many options. We have open source software we can look at everywhere. A lot of us use Juice. And my suggestion is if you use Juice, just use the Juice oversampling library at first. And the reason is you want to practice on getting the big wins. Pick the right design decisions within there. It's all packed in. You can set it and be like, I want to use FIR. Here's how much attenuation I want. Here's my transition bandwidth or cutoff frequency. And you're good to go. And then if you have a particular need, you're like, oh, the filter doesn't get steep enough, or I want to see if it can be more efficient, then you know what you want. Now you can go search for something that's real intensely great at that one thing. But you don't know what it is you want until you try it out, and this Juice library has kind of all the variables you need. Now, one thing that's not true about the Juice library is it does not automatically set up the filters to have the most optimal performance per layer. So it will reuse the same filter for every stage. So you should use its ability to specify, you get to specify each oversampling stage. Use that feature. You can also use it to experiment, but honestly, I would just use the formula I dropped in the previous page. Now, if you don't use Juice, there's other options available to you. If you want a low latency product, HIIR, which I mentioned briefly, is great. It's just, you're gonna wanna have a discussion with your build engineer first because integrating it is not particularly fun. And Signalsmith DSP is also a great library that is available and open source, and you can use that for FIR. There are other ones out there to try. And when you're using any of these libraries, it's important to look at the arguments you pass in and kind of normalize it to my transition bandwidth, my cutoff, and my attenuation, right? They might use slightly different arguments for setting them up, but that's where we end up. So let's talk about where you might want to oversample in your signal chain. One option is you could just oversample the whole damn plugin. That's totally fine. In fact, I actually think a lot of the time it's good because I'm about to go over a bunch of things that might happen if you don't do that. However, you can also just oversample over your nonlinear math, right? Because I said if your math is linear, you don't have to worry about, well, there are some situations, but for the most part, for distortion, you don't have to worry about aliasing as a problem. Right, so you need to balance CPU efficiency with the difficulty to maintain your plugin because it could get really hard and there are lots of these. Let's get into them because they're not particularly fun. The first of all, latency compensation. Some of these libraries even don't report the latency correctly to you. It's up to you to check and measure the latency and report it to the host. Otherwise, your users are gonna get annoying problems where their tracks are no longer synced, things like that. Also, when you do change the latency, there's often pops and clicks that happen, so you probably wanna duck the volume. Phasing issues. So if you are planning on making like a plugin that people would put on a send as opposed to an insert, you probably wanna use linear phase, but also within your own math. If you're mixing non-oversampled with oversampled math, you might have filter coefficients that you have to calculate differently because they won't add up to the same. There might be issues if you don't calculate your delay correctly because how many samples are we delayed if we do oversampled processing at 4 times and we delay by 1, after we downsample again, we're like a quarter sample off? That gets a little tricky, right? So this can be a little, you have to compensate for this. There are several tricks. You could intentionally add a delay line in your oversampled code so that it lines up on the integer line and it's easier to recombine the signals and stuff like this. But you gotta keep track of the parts of your code that do this. Sample rates and buffer sizes. If you're mixing things, you are going to do buffer overruns if you're not careful. And unlike Wile Coyote, you don't even get the second of like gravity letting you stay up. It's gonna immediately crash. Hopefully your QA department will find that. But keep track of it. If you're gonna do this, you'll have to be like, all right, this is an oversampled buffer, this is not an oversampled buffer. I happen to reuse this, I probably shouldn't have, these are the problems you'll run into. Again, filter coefficients, and again, delay line measurements. You just have to remember which things happen in which realm and remember to compensate when you come back in. High sample rate projects. Some of your users are running in 96K, 192K. Mastering engineers might do something different than a producer. You don't know what your user's using. So you have to make things configurable. I mean, you could say, oh, I'm always gonna run at this one rate and I'll just automatically upsample or not, but it's probably best to make things configurable in case you just didn't think of something. So you'll need to test the math that it works in these different configurations and make sure that it's compatible as well. Headroom is another consideration. This is especially important if you're writing like a clipper or a limiter that's at the end of the phase. You're going to care about the overshoot that happened. It's also known as the Gibbs ripple. And yes, even if your filter has no ripple, even if you have a Bessel or a Butterworth filter, the low-pass filter will still cause overshoot in the waveform that it is processing. If you're doing dynamics processing, like in your plugin pipeline, after you've finished oversampling, you might care. Live chaining oversampling settings, you should make this possible. And the reason is people will want to do a live comparison. This is a little bit less important, but because someone could always bounce out multiple copies of what they're doing and compare it. But it's really nice to allow your users to just like pop in the changes. But if you're doing that, you got to remember, do not allocate any memory in the audio thread. You have to find a way to do this work and allocation in some other thread and then pop it in when you can. And there's some DAW-specific issues to this. I noticed in Logic, I think when I change something that changes the latency, I have to stop and start the transport. So, you know, when you're checking your work, you want to look out for these problems and also maybe notify your users, like, hey, if you're using Logic, you know, got to do this. Now I'm going to go to one that people don't talk about very much, but it's actually really cool. It's a stupid secret. And I call it a stupid secret because I don't hear about it a lot, but you might be able to get a lot of gain from this. I'm calling it the aliasing staircase. There is a problem where if you have multiple nonlinear processes, which is pretty common, after your first nonlinear process, you've made higher frequencies in your signal, right? And then if you have another nonlinear process, you're pushing those high frequencies even higher. So every single nonlinear process you do, you're climbing up the stairs, and sooner or later you're going to start bouncing back and things are going to get hairy. All you got to do is put a low-pass filter between your nonlinear processes so that we don't climb the staircase. And that might actually get you better performance. So if you've been trying oversampling and you're not getting results that you like, and you have a lot of nonlinear processes, you can try this technique to see, oh, well, does that get me where I need to be, or do I really have to go ham on like some crazy oversampling thing? It's definitely cheaper than oversampling and downsampling a bunch of times. I'm just going to say really quickly, there's a couple of other things to think about. There's something called polyphase, FIR. If you look, it's a complicated thing where you have one filter response and it knows how to both do the padding and the filtering at the same time, which sounds great in theory, but you can go to KVR and hear our forefathers arguing at great length about whether or not it's worth implementing. I did not find a lot of solutions that just sort of provide this great out of the box, which is why I'm not recommending it. However, I do think that if for whatever reason your application is that CPU usage is the absolutely most important thing, none of the other things matter, that it's probably the case that an IIR filter, which is really efficient for the first stage, and then followed by an FIR that handles all remaining stages, is a great solution for that. Again, I do not know of a library that does this, so this is a little bit theoretical here. I just wanted to bring it up as a thing. There are some things you might want to use oversampling for if you don't have distortion as your problem. One of the most common of these is filter cramping. If you use biquads, as you use frequencies that are higher and higher to Nyquist, the filter response starts to crush, it starts to warp, and no longer really represent very well its analog counterpart. And that's a problem, but you can solve it by, again, moving the Nyquist up. So as a generic solution, oversampling is good for this, but it's not the only solution. I just dropped some names in here of some academic papers you can read that are different ways of generating filters that compensate for this problem, so you don't have to double the samples. What's also interesting is if you happen to use a linear filtering technique, you don't need a destination filter anymore because you haven't added any harmonics. You can just remove the extra samples and be done with it. That's pretty cool, but these techniques are probably worth checking into. And I'm gonna bring up Signalsmith again because he has a page, if you click and look at this, that compares some of these different techniques so you can sort of see what you're getting and how it might help you. There's also other techniques for anti-aliasing. Anti-derivative anti-aliasing is a great one. I first learned about it by reading is it Jayton or he's gonna, anyway, Jayton's blog posts and a paper he wrote, I guess when he was at Stanford. But the thing for this is that it requires specific math for whatever your nonlinear process is. So you have to allot time for whoever does the math in your organization to work that all out. right? And it pairs really well with oversampling because it handles some of the stuff really well, but then as you oversample, you kind of get this cumulative effect that's really great. So I would look into that. I provided a link there. If you make a synthesizer and you want to create waveforms, we have BLEP and BLIT. I put some links in there. And you could always just do a crossover and only do your nonlinear math on the low band. I mean, that's actually how a lot of bass enhancers work. It's sort of like a cheesy way to do anti-aliasing because you're not doing your process on the whole signal, but it's definitely something to look into, and it might be right for whatever it is you're doing. So this brings me to one more thing, which is high sample rate projects. Is it better to just do this? And this is what's crazy, because I've given this whole talk, and I actually think that it is. It'd be much better if the user just said, I care about latency or I don't, and then, there is no up and down sampling and filtering and decisions that are made by every single plugin on every single track in the chain. That would actually be really good. But the problem that happens there is the aliasing staircase, right? It's no longer under your control because now we have multiple plugins that are all doing this, right? And you don't have any way to put some sort of filter in between them, right? Dan Worrell, who's a good influencer, he has a video on this and he proved like, hey, if I take one of my favorite plugins and I oversample it, and then I take, I don't remember what the product was, I think it was Reaper, and you do an oversampling channel strip and I stick all of them not oversampling in the oversampling channel strip. And I take spectrograms of it. It looks worse in the oversampling channel strip. So why would I ever do that? I should just oversample and downsample 50 times. So I have a proposal about how we could make things better for the users that we have, which is, and I have no interest in making a DAW or an oversampling channel strip, so I'm just giving this away. But like, if that's something you do, it would probably be a good idea to just stick a little button next to your inserts that allows the user to stick a 20 kilohertz low pass filter in between your plugins. I mean, why not? You just click the plug, it's better. And it prevents the aliasing staircase from building, and people don't have to turn on oversampling on every plugin that they put in their chain. The real problem is just if you tell someone that they have to do that and don't put that button there, they're just not gonna drag low pass filters between everything. It's a pain in the butt. No one's gonna do it, and I'm not gonna pretend that anyone's gonna do it. But we could make the situation better, and so we should if we can. As a stopgap, if this doesn't happen anytime soon, we can also just build it into our plugins. We could say, hey, I noticed that your sample rate is above 48K, so I'm gonna give you the option that I can just drop a low pass filter on it when I'm done, just to be nice, so we don't climb this aliasing staircase. I think that would be great, and then as computers get faster and faster, there's fewer barriers to just not oversampling 50 times and causing all this stuff. So at the end of the day, you're going to have to communicate what you decided to do to the users that you have for your product. This is tricky because some people spend a lot of time looking at charts and graphs, and it might be the kind of user you have. And I'm gonna tell you right now, and I think I've made this mistake in the past, you're not gonna win any fights telling someone they can or can't hear something. I mean, I know I can't hear above like 17,500 hertz. Someone might claim they can. I know I can't hear some stuff that's like below negative 50 dB. But we stack plugins, right? We stack plugins, the stuff adds up. We stack tracks, lots of mixes. So you don't want to get into the rabbit hole of getting in an argument with your users. That's really important. You also want to internally notice when something looks bad in a tool like Plugin Doctor, because someone is going to bring it up if your plugin is successful. Someone's going to bring it up and talk about it. If you can make it look better, you should. I'm not saying it's the most important thing, but if that's your audience, it's probably worth looking into. And if you still have someone that comes at you for some stuff, even though you've done the best you can to make the best decisions for your product, first listen to them because they might be right, but you do have to stand behind your choices and not attack the user's point of view when they're talking about it. So instead focus on like, hey, I made this the best that we could for what we're doing, and we think it's the right decision, and that's what it is. And some people, you just can't please everybody. It's very tough for us, I think, that we now have like this new line of scrutiny, but we need to use it to our advantage instead and help it, like our plugins actually do better. There are some situations when, you actually do get told something that you didn't know and you can now improve your product. So the knee-jerk reaction is something you gotta like flush away, listen and just, go with it. So that concludes my talk and time for Q&A, yeah?